Hi viewers, in today's class, let us solve another example on stepped bar. The question is to determine the diameter of the aluminum portion so that the total elongation of the stepped bar shown in figure is limited to 0.98 mm. This stepped bar is subjected to different loads. Now, the dimensions of the various portions are given, except the center portion, the aluminum rod, the diameter is not given. First portion is steel and it is 280 mm long and 60 mm diameter, and its Young's modulus is also given 200 gigapascal. Second portion is made out of aluminum and it is 320 mm long and its diameter is not known, and its Young's modulus is 70 gigapascal. And the last portion, we have a copper material and its diameter is 40 mm and the length is 250 mm. Young's modulus is 100 gigapascal. Now you are also given the total elongation when the bar is subjected to these loads. Now with this data you should find out what should be the diameter of the aluminum portion so that the total elongation is limited to 0.98 mm. So instead of finding out the total elongation, we are finding out one of the unknown. It can be anything, like it can be the diameter or it can be the length of the one of the portion. One of the unknowns we can solve. So in this case it is the diameter instead of the total change in length. Now let us work out. To find out the forces in various sections, let us take a section plane here and sum up the forces on the right side, taking the leftward as negative and rightward as positive. So I am taking the section plane in the first portion and summing up the forces on the right side. Okay, leaving this, whatever it's on left side I am leaving and taking the right side forces that will reveal the internal force. So minus 40, okay, plus 50 and plus 200. So that will give the force in the first section, that is in the steel portion. I am representing this by subscript 1. You may even give a subscript S for steel and A for aluminum, like that. Now we got the force in the steel portion. Now let us come to the aluminum portion. I have taken a section plane and seeing the forces on right side. We have 50 kilonewton rightward and 200 kilonewton rightward. So 50 plus 200, which will give 250 kilonewton. So you got the force in the aluminum section. Now let us go to the copper section and take a section plane there and see the forces on right side. This force is not considered, it's applied at the junction, so it is not coming anywhere. If you take the section here also, this force should not be considered because point of application is at the junction. So you need to consider only this force 200 kilonewton, which is right side of the section plane. Okay, so and since it is acting towards right, it is positive, so plus 200 kilonewton, that is a force in the copper section. So we understood all the forces, internal forces in all the three sections. Now let us tabulate the data. So the P1, the first section, we got the forces 210 kilonewton. We can write it as 210 into 10 raised to 3 Newton. Everything has to be converted into Newton. Force unit I am using Newton. So P2 is 250 kilonewton. It's 250 into 10 raised to 3 Newton. And P3 200 kilonewton. So 200 into 10 raised to 3 Newton. Diameter of the first portion is known, it is 60 mm, and the last portion D3 is 40 mm. D2 is unknown, that is what we need to find out. Okay. Now length L1 is 280, L2 is 320 and L3 is 250 mm. All dimensions in mm. Now E1 the Young's modulus of the first section, that is steel, it's given as 200 gigapascal. You can convert gigapascal into Newton per mm square by multiplying by 10 raised to 3. We need to convert into Newton per mm square because force unit we used is Newton and length is mm. So we need to convert into Newton per mm square. So gigapascal we can convert into Newton per mm square by multiplying by 10 raised to 3. E2 is aluminum, Young's modulus of aluminum. So it is equal to EA. Okay. So it is 70 gigapascal, 70 into 10 raised to 3 Newton per mm square. A third section is made out of copper. So E3 is EC is equal to 100 gigapascal, or 100 into 10 raised to 3 Newton per mm square. So these are the known data. Now let us find out the total elongation. So individual section elongation you can find out, but second section you cannot find out the elongation because diameter is not known, but we know the total elongation. So let us calculate the elongation in the first portion. We know the force, length, area and the Young's modulus of the first portion. So force we understood 2 ton into 10 raised to 3 Newton and length is 280 mm. A1 is, since it is a circular cross section, area of cross section has to be calculated as pi by 4 into diameter square. Diameter is 60, so 60 square. And the Young's modulus is 200 into 10 raised to 3. So it will work out to 0.10398 mm. Now delta L2, the formula is P2L2 divided by A2E2. Out of that A2 is unknown since the diameter of the aluminum portion is not known, but you can use it as pi by 4 into D2 square. P2 we know it is force in that section is 250 kilonewton, which is 250 into 10 raised to 3 Newton. Length of that portion is 320. We have substituted that. Area we have substituted in terms of diameter, so it is pi by 4 into D2 square, where D2 is the diameter of the aluminum portion. Now E2 is 70 gigapascal, so 70 into 10 raised to 3 Newton per mm square. You can reduce this into 1455.13 divided by D square. Okay. Now delta L3 is P3L3 divided by A3E3. So P3 is 200 into 10 raised to 3. L3 is 250 mm. And we know the diameter there is 40 mm. So area of cross section is pi by 4 into 40 square. And Young's modulus of copper is given as 100 gigapascals or 100 into 10 raised to 3 Newton per mm square. So you can calculate as 0.3979 mm. So we got the change in length, in this case elongation, because all are subjected to tensile loads. So change in length in the first portion and last portion, that is in steel and copper. But aluminum we don't know, we only in terms of diameter we will get. Now if you add all the three, you should get total elongation, which is 0.98. So let us add and equate to 0.98. So total change in length is given as 0.98 mm. So that is delta L is delta L1 plus delta L2 plus delta L3. Now this is known, total elongation is known, so 0.98 mm. Now we have substituted what we got for delta L1 and delta L2 and delta L3. Now if you work out this, you can solve for D2 square and then find out D2. That is D2 will get as 55.167 mm. So you require a diameter of 55.167 mm to limit the elongation to 0.98. So when you use this diameter, the elongation will be 0.98. In case if you reduce the diameter below this, then the elongation will be more, and if you are increasing the diameter, then elongation will be less. So you want to limit the elongation to 0.98 mm. So you should have a minimum diameter of 55.167. It should not go below this. Usually you will not get a customized diameter like this. So you need to go for standard which is available, but you need to select the higher dimension. And so if you select diameter 60 mm for the aluminum portion, then definitely the elongation will be less than 0.98 mm, and we want to limit that to 0.98 mm. So if it is anything less than 0.98, it will be okay. For the sake of the theoretical calculation, T2 55.167 mm, and that is our solution. Okay. So the minimum diameter required is 55.167 mm. That's all for today. Thank you for watching.